everyone, and welcome to another FLAN talk. Today we have Olga Golovneva with us on their paper on contextual positional encodings, learning to count what's important. She is currently a researcher at Meta in Washington, D.C., and you can take it from here. Thank you for being here, Olga.
Thank you. Thank you for introducing. Yeah, I'll be talking about our recent paper, Contextual Positional Encoding, Learning to Count What's Important. This paper was written with my amazing co-authors, Tian-Lu Wang, Jason Weston, and Sinbayar Subhatar. Let's start with motivation. Many common data sources, such as text, audio, code, timeline of events, ordered sequences. When we process such sequences, the order information is clearly critical. In the case of text, position information is vital, not only for decoding meaning between words, but also necessary at every scale, such as sentence, paragraph level. If we look at the examples on the slide, if in the sentence, the dog chases cat, if we switch dog and cat places, we'll get the cat chases dog. So the meaning has changed. Another example I can think of, if you type something in Google search and you search for blue sky, probably you will get some pictures of the blue sky. While if you search for sky blue, probably you will get something about colors or shades of blue. Changing the order of words can change the entire meaning of the sentence, and we need to pay attention to it. On the left picture of this slide is a transformer architecture. It's the main backbone of current large language models. It relies on the attention mechanism that inherently lacks ordering information and treats sequences as sets. I know you recently have had a presentation on hard attention, so you kind of had this introduction, but I will focus on position encodings here rather than attention mechanism itself. But there will be some overlap in background for sure. So since attention mechanism treats tokens as sets, we need to have additional mechanism to encode position information. In the example on this picture, position encoding achieved this by assigning embedding vector to each position and adding it to the corresponding token representation. But in general, positional encoding methods can be categorized into two main groups, absolute and relative. Absolute position encoding simply adds the vector representing an absolute position to the hidden states, usually after token embedding. Or sometimes it can be implemented by embedding layer that assigns unique learnable vector to position value, or through mapping that uses sinusoidal functions with different frequencies. So there can be different methods, but they all rely on this absolute position of the token we are looking at. Relative positional encoding depend on the token position that being attended to in the addition to the current token. Therefore, it has to be implemented within attention layer so that we could look at the relative token attentions. Fixed functions can also be used, such as rope or rotary positional encoding. That's probably the most common positional encoding method applied currently in transformers. It's added as a rotation matrix applied to keys and queries, where each pair of keys and queries rotated by a certain angle. So what's the issue? We have so many positional encoding methods. One common feature of these positional encoding methods is that they rely on tokens as units of measurement. Our token is variable unit. It can be a whole word, it can be part of the word, which is most common, or it can be even a character, depending on the tokenization method. The position variance increases for more abstract elements, but still semantically meaningful that we interpret as people who use language, such as sentence, which can have 10 to 1,000 to hundreds of tokens. Therefore, token position is not suited for general position addressing, such as finding certain word or counting like certain word in a certain sentence. Like in the example on the right, we asked GPT-4 and Llama 2 70 billion chat to count certain words in the last sentence. So here the model has to first split text by sentences, then count from the end and attend only to the last sentence and find certain words and count them in that sentence. The task can be made even harder further if we ask to count certain words in the last two, three, and so on sentences. So the longer the context, the harder it's for model to attend both to the words and sentences simultaneously. So in this example, both models failed to count word Alice or to count word book in the last sentence. They both produce wrong answers. To overcome these problems, we introduce contextual position encoding, COPE. COPE compute gates values conditioned on the context first. That's why contextual position encoding. Then we use these values to assign position to tokens using cumulative sum. This allows positions to be contextualized and represent the count of different units like words, verbs, and sentences. COPE operates on each attention head, and so it can attend to different position types on each head. Like one head can count words, the other head can count sentences, another paragraphs, and so on, and so on, or any other abstract units you might need for your task specifically, or it was learned during pre-training. In this example, attending to the last sentence using relative positional encoding is challenging. And the best it can do is this decay, gradual decay attention shown on the top. COPE can count the sentence endings and simply attend to position 0 and increase counts each time it sees the end of the sentence token. And thus it will differentiate between these different abstract semantic units. Let's look into how it works in detail. In COPE, positions are measured in a context-dependent way rather than being a simple token count. The method works by first deciding which tokens should be included when measuring distance using the context vectors. For example, if the task to count sentences, then we need to attend to this period, or not just periods, but just end of sentence tokens. To do that, we compute gate value for each query and pair, which is part of the regular attention calculation, actually. But then we apply sigmoid function on these values. A sigmoid function outputs values between 0 and 1. Here, the gate value of 1 means that the key will be counted in the position measurement for given query, while 0 means it will be ignored. For example, to count the sentences between certain tokens like I and J, the gate value should be 1 for only sentences, separation tokens. The gates also condition on the query so that each query can have different position measurement if we need for some task. Next, we compute position values by adding the gate values between the current and target token, cumulative sum, in other words. Note that if gate values are 1, then this cumulative sum just becomes regular token-based relative position encoding. Thus, COPE can be viewed as a generalization of relative position encoding. In general, however, these values P can be the count of specific words or word types, like nouns or numbers, the number of sentences, other concepts usable during training, and they will have different values depending on what we are attending to. Here's one tricky part. Unlike regular token position values, our position values P are not restricted to integers, and they can take fractional values due to sigmoid function we applied before. This means we cannot use an embedding layer, like traditional embedding layer that embeds integers to convert position value to vectors, like we do in relative PE. Instead, we use the interpolation between integer values. First, we assigned a learnable embedding vector E for to each integer position between 0 and whatever the maximum context window length we have. Then the embedding for each position will be a simple interpolation between two closest integer embeddings. Finally, these embeddings are added to the key values to compute the attention rates. To summarize, COPE compute gate values conditioned on the context first, then uses them to assign position to tokens using a cumulative sum. This allows positions to be contextualized and represent the count of different units like words, verbs, sentences, paragraphs, and so on. COPE operates on each attention head, so can attend to different position types on each head. In this example, attending to the last sentence using relative positional encoding challenging, and the best thing can do is decaying attention. COPE can do sentence ending, can attend to sentence endings instead. Now some notes on COPE, how it can be changed and applied in different way. Like from this equation on the top where we calculate cumulative sum, we can see that the maximum value for P is restricted by the context size, which means we would need like context size plus one position embeddings. That would include position 0, like per initial query. However, if the gates are sparsely activated, like if we count something big like sentences, paragraphs, we can cover the whole context with much fewer positions. So we don't need the whole context size, and we can limit our position according to some top value Pmax. Like in this example in the picture, just Pmax to set Pmax to 1 just for illustration purposes. And then once our cumulative sum reaches this value, we just crop the rest of the values and count it from right to left. This also can be useful if we know that the long positions will not matter, and we don't want to actually learn their meaning. Now the multi-head extension is straightforward. Each head will have their own positional encodings, and it can do them independently, same way as it does attention independently. Keys and queries vectors different between heads, so that means they can implement different position measurements. For example, head 1 will have keys that turn all the gates on so that it counts tokens. Head 2 will do word beginning tokens to count words at position. Head 3 will attend to sentences and so on. While the position embeddings are shared between the heads only, we also experiment with position embeddings that are shared across the layers as well. Now that's it for the theory. Let's move on to experiments. So first we experiment with toy tasks where we know traditional positional encodings will fail. One of these tasks is flip-flop task. There was a recent paper released early last year exposing attention glitches with flip-flop language modeling. That was a large inspiration for our approach. This modeling task exposes the failure of transformer models to capture robust reasoning over long-range input sentences. The input string is pretty simple. It consists of alternating sequences of instructions: write W, read R, or ignore I, each followed by one bit of information 0, 1. So the model needs to memorize this bit of information. If it follows W, if it follows write, recall it if it follows R, or just ignore if it follows I. It's guaranteed in this task that all strings start with W and end with R. So always the task is to recall whatever was written last. Like in this example, the expected output is 1 because 1 was written last, was made last after W. So to solve this task, the model has to be able to sharply attend to the latest occurrence of W symbol, the position of which varies between sequence due to ignore instructions. So here on the bottom, I added the link to the talk on the hard attention that I had recently. He was also talking, the presenter was also talking about counting tasks. There, we will consider them next. The problem with sharp attention here, we actually tried sharp attention. I think maybe authors also tried sharp attention on this task. It fails because sharp attention cannot do this counting. Um, and I don't have the meaning of the last. Um, so we use simple setup decoder as just repeating the setup from the paper. Decoder with dimension 256 for heads for layers. The task is defined for two test sets, in distribution and out of distribution, where the later increases the distance to the last W, to the last writing, by increasing the number of ignore instructions. So that like we change in the probabilities of reading ignore symbols. So here we compare with absolute positional encodings, rope, and our method. Our method can solve the task and achieve faster convergence, which probably can be seen on the right. The cope are blue lines, and it goes to zero faster, like almost closely after 2,000 of steps, it's already starting converging to zero, unlike all other methods that are much, much slower. So COPE can not only learn in distribution, but it achieves significantly better result in out of distribution task. The current existing position method failed to provide this property. This is possible because COPE allows the model to attend to the last seen position of that specific token by incorporating their counts in the position embedding using their keys, by making the gating function switch on only on these specific tokens, right tokens. For example, if the gates are 1 only for W tokens, then position 1 will correspond to the last W instruction. In contrast, relative position encoding struggles to isolate last W and with its decaying position function, especially if the position is unknown and far away, which results in poor out-of-distribution generalization. Next task, synthetic task, toy task, is selective to copy task. It was introduced in Mamba paper, where they also showed that classic transformers fail on this task. This task requires context-aware reasoning for selective memorization. Mamba can do this because of its sequential nature. Traditional transformers with rope embeddings cannot. In this task, model is given a sequence of tokens, like shown on the left, input D, B, and so on. And the model is asked to copy all tokens except one blank token, like token B, on noise token. In our experiments, I think we repeat the Mamba setup as well. We use 16 characters. We use the alphabet of 16 characters. And the output sequence length is set to 256. Six disappears from the slide, and vary the number of blank tokens. So we also have here in distribution and out of distribution tasks. So and vary the blank tokens in distribution and out distribution. We train another small model, decoder with dimension 64 to heads to layers, to heads, to layers, and report a test error after 100,000 of steps. So as we can see, the in distribution test set, our method can solve the task with 0 over error rate, while other methods fail to do so. It generalizes very well in out-of-distribution task. It doesn't make any difference on how long the task is. It was able to attend to this noise token and just isolate it because it's contextualized, so it increases position each time it sees this token. It's aware of its embedding, while other methods completely fail to do this, especially if you look at the rope rope just leads to 100% error rate. Cannot do this task on out of distribution. Now to counting task that I already mentioned before a couple of times. That's we start with symbolic counting task, and we'll also generalize it to like more natural counting task later. But we start with a simple one. Counting task is more challenging than simply recalling, as in two previous tasks, because it requires more uniform attention over a certain span, if we need to count for several tokens, for example. Like to count verbs in the current paragraph, the model needs to attend to the verb tokens roughly equally within the current paragraph. Thus, a simple recency bias that operates on relative positional coding, that's common for relative positional coding, will not work because it suppresses verbs that occurred earlier due to its decaying nature. To demonstrate this in controlled setting, we introduce a symbolic counting task where the context is a sequence of operations of three types: set variable to 0, increment it, or do nothing. In this example, we have on the top pass, then we set variable a to 0, then we do nothing, then we increase it by 1, do nothing, increase by 1, and then we expect the model to output the count of the value of the variable a. Similar to flip-flop task, it's guaranteed that at the end of each sequence, we will have this printing operation specifying which token we want to print out, because it can be more than one variable. We experiment with tasks with 1, 3, and 5 variables in the context. This is a fairly simple task. The model just needs to count these plus plus operations followed by the certain token. In a more challenging version of this task, we mix multiple values and we experiment with different weights for pass operation or ignore operation. We have, again, in distribution task and two out of distribution with shorter and longer context, where we increase or reduce the probability of the pass operation. And in our controlled experiments, we also guarantee the output is always less than 10 to just make it even easier.
I had a quick query here. So for the long context, so like how many tokens that you covered here?
Up to 512 tokens.
Okay, okay.
But the context length varies because it's non-deterministic task. We have certain probabilities of weights for each token, but the upper bound 512.
Oh, cool. Thanks.
So we use decoder with dimension 256 for heads and for layers. We experiment with absolute and relative positional encodings here. And we can see that the more variables we introduce, the more struggles it brings in for the model to attend to specific token and count them. Absolute positional encoding performs worse than others. The best performance comes with cope with a perfect score of 0 for one variable case. For out of distribution generalization, relative positional encoding show poor generalization, cope generalize well. We also experiment with amount of training data, and we look at the validation error. We see that cope, as we train, cope converges much faster or generalizes or learns this task much faster than relative positional encoding. Now let's move on to language modeling tasks. So that's it with synthetic tasks. We train two medium-sized language models. One on Wikipedia dataset, the other one is on code dataset. And we experiment with different architectures also to see how it will change. So Wikipedia based model is GPT-2-like model. Code model is Llama 2-like model trained on their mix of coding data. And we look at the validation and test perplexities for both tasks. And we see that COPE showcased lowest perplexity across both models on both tasks. What's interesting here also is generalization to longer context. We test how well COPE generalized to context longer than it was trained on. As COPE assigns position conditioning on context, it's capable of distributing them to a much larger number of tokens. While the number of tokens was fixed during training, the number of positions will vary depending on each sample. Thus, it's possible that tokens outside training span still get position values that are within the maximum limit Pmax, and it will show much better generalization. As we can see in the picture, the green line, the perplexity is the lowest. We also show how COPE combined with relative position encodings, they don't interfere with each other, they can be applied together, and also can lead to better performance on Wikipedia. Then we move to scaling our model. We train Llama-like model on similar data mix as was in the Llama paper, but we train 1.4 billion model from scratch. Here we show the validation perplexity on Wikipedia and C4 datasets. COPE shows faster convergence. In the beginning, you see that the validation perplexity of our method is slightly higher, so it needs some time to catch up to learn this positional encoding. And then when it's done so, it outperforms rope and with almost constant perplexity improvement as it keeps training. Then we experiment with introducing a new word count task. In this task, the model is asked to count how many times specific word occurs in the last K sentences. So what I mentioned in the beginning, like with the example I showed with GPT-4. So to run these experiments, we use tiny stories dataset. We generate 2 million stories for training and 20,000 for validation. To make the task more challenging, we randomly concatenate 3 different stories to form much longer samples, because tiny stories, the context length is within like 1,000, 1,500 words. No, tokens, I'm sorry. So we extend the context artificially by concatenating them, and then ask to count certain words in certain sentences. We here report the results of fine-tuning our 1.4 billion model on this task. We see that COPE significantly improves over standard embedding approaches, boosts model capabilities on the standard task. To see how difficult this task is, we also tested Llama 3.1, 870, 400, and even GPT-4 on this task, and we see that the performance is far below 20%, not far below 20% accuracy. We further test how we also trained 7 billion model. We scaled further to 7 billion model. That's the largest we could train given our resources. And we compare rope and COPE combined with rope model. Here we also tested if new capabilities introduced by COPE will interfere with performance on standard benchmarks. And we can see that we bring in slight improvements on average across standard tasks. These standard tasks are in general short context tasks, and they don't involve any complex semantic questions over the context. So we don't expect to see any significant boost here, but even though these tasks are very simple and already solved pretty well by standard embedding, COPE still brings in some improvement. So this is the last slide of the presentation. To summarize, we introduced COPE, new position encoding method for transformers that takes into account context. We showed that this method can count distances, and it can do so in different heads. By the way, yeah, on this picture, we can see how the attention maps for COMP on wiki text data set. And we can see it. So these are from different heads. We can see that actually COPE focuses on paragraph and section, even though it was not trained to do so. It was trained on regular language model and task, but it learned different abstractions since COMP is contextualized. And on the left, tokens are separated by new line tokens, while the right is separated by section titles, such as this description, which is kind of cool finding that we saw in our experiments. We also showed that copes of counting and copy tasks that standard transformers cannot, or I should say standard positional encoding methods fails to do. And we showed better perplexity and improved accuracy numbers and language modeling encoding tasks.